All right, everybody. Good afternoon. Thank you for joining us for this webinar. My name is Kevin Topolsky, and I am also joined by Jamie Key, who is also visible through this Zoom meeting. Both of us are hydrogen infrastructure analysts at NREL, and we will be presenting upon a tool that our team has developed called Blending Pipeline Analysis Tool for Hydrogen. Before we move ahead, this webinar is being recorded, and it will also be posted on NREL's website at this link below. I definitely anticipate that many of you will have questions as we go along this webinar. If so, please, I would like to direct you to point those questions to the Q&A box or as part of this Zoom webinar. Our team will do our best to answer these questions during the Zoom webinar or at the end of this given hour. So our webinar and agenda will consist of these 4 parts. I will be presenting the introduction. Jamie here will be presenting the later 3 sections of this webinar. So BlendPATH is a NREL developed pipeline tool that is specifically developed to allow users to answer 2 key questions for blending hydrogen into their natural gas transmission pipeline networks up to X% hydrogen in pipeline gas. The 2 questions that we developed the tool to answer are: what are the modifications to a natural gas transmission pipeline network to enable pipeline transport of X% pipeline gas with X% hydrogen? What are these modifications that are required for this? And then also, what are the incremental capital investment and operating expenses that are required and are associated to these given modifications? We developed BlendPATH to target the application, or basically the target application at the initial project assessment stage for transmission pipelines. This is where the pipeline owner or operator is gathering pipeline design and operating records for the system that they are looking to assess. The intent with us developing the tool for this stage is to provide users with a understanding of the most promising opportunities for hydrogen blending within their given pipeline systems. Do this very early on before the user proceeds with more higher cost pipeline evaluations, such as that includes detailed pipeline inspections. To the right here, we have a framework overview of the BlendPATH. You can see that this is a mix of multiple models that help us get from our known inputs, which are the pipeline design records and operating records, as well as a user-specified amount of hydrogen pipeline gas. We can take these inputs and proceed through this framework such that we arrive at the end use or at our outputs, which are the pipeline network modifications, as well as the financial assessment that is related to blending hydrogen within this modified network. Next slide. So before we go deeper into the technical content for this webinar, I would just like to make clear that this webinar is specifically focused on the initial release of BlendPATH and its current capabilities as a research tool. And given this, BlendPATH is subject to limitations. Currently, BlendPATH analysis is limited to linear pipelines, specifically where there is one gas supply, where we assume that that's where hydrogen blending is taking place, and this gas is being transported downstream to multiple offtakes or end users. Depending on the pipeline network that's being analyzed, BlendPATH may not be capable of analyzing blends up to 100% hydrogen. This is a factor that depends on the hydraulic characteristics of the examined network. But for this given webinar, we will be featuring an example where BlendPATH can examine blends up to 50% hydrogen. The initial release of BlendPATH does require a commercial integrated energy system modeling platform called SAINT to perform some of the underlying gas pipeline hydraulics. I'd like to note here that an additional version of BlendPATH with a open source gas pipeline hydraulic model is currently in development to provide more access. So last but also the most importantly, BlendPATH itself does not qualify pipeline networks nor modifications thereof for hydrogen blending, despite using a industry standard called ASME B3112, the industry standard for hydrogen piping and pipelines in its assessment. Pipeline network qualification for hydrogen blending will require additional evaluation as specified by this industry standard that is independent of BlendPATH application. It's the sole responsibility of the pipeline owner and operator to ensure that their pipeline network qualifies for this standard and any other relevant regulations, and that any present defects within their pipeline network is acceptable or are acceptable at the operating pressure chosen for blending hydrogen. But with that, I'd like to take a pause here and transition this to Jamie. Jamie, can you take it from here?
Yeah, thanks, Kevin, for the introduction. So next, I'll be talking about the BlendPATH methodology, kind of the inner workings of BlendPATH. Next, going on into installing and running BlendPATH, and then finally followed by a live demonstration. BlendPATH apportions the model pipeline network into segments for design pressure rating and pipeline network modification. The first step to BlendPATH is to first start with a converged simulation instance of a natural gas pipeline network operation without hydrogen blending, and that's the analysis starting point. What this means is the input files need to be valid such that it is a network that solves and gives reasonable hydraulics. Without that, then the following analysis is dependent on that, so it needs to be on the same level. Within the pipeline design assessment module, BlendPATH then divides the model pipeline network into separate pipe segments. And what we define a pipe segment is as a group of consecutive pipes that can withstand the same design pressure throughout. And one example, or one reason for that is for line packing purposes. A pipe segment can be delimited by a various number of features. Some of them are compressors, pressure reduction stations, or changes in nominal diameter. For example, we have a fairly simple network shown below, where we have 2 compressors, 4 pipes, and then a supply on the left side and 2 offtakes on the right side. As I mentioned, a compressor can be a delimiter. So between pipe 2 and 3, we have a compressor. So we combine pipe 1 and 2 and put that into segment 1, and then segment 2 it contains pipe 3 and pipe 4. So even though we're analyzing the pipeline network as a whole, we do the modifications on a segment by segment basis. The pipeline design assessment module identifies design pressure violations according to the user specified ASME B31.12 design option for blending. So after the network has been segmented into segments, we then run BlendPATH, run the operating conditions to make sure we meet end user demands. And what this means is that we're running the hydraulic model in SAINT with hydrogen blended in, and then we're verifying that we can meet end user demands and pull out the operating conditions. What operating conditions could be pressure, flow rate, and compressor fuel usage. One constant within BlendPATH is that end user energy demand has to be satisfied. So the modifications are performed such that those are met. Within the pipeline design assessment module, we assess and update the pipeline segment design pressures, or also known as the maximum allowable operating pressure, based on the user-specific ASME B31.12 design option that Kevin had introduced. ASME B31.12 allows for 3 design options to qualify and rate pipelines for blending. And these design options require varying extents of pipeline material characterization for qualification. If we look at table 1, this outlines a few different design factors for design option A and design option B within ASME B31.12. And this can depend on the location class. We also consider a third design option, which limits the design factor to 0.4. And within BlendPATH, we refer to that as no fracture control. BlendPATH identifies which segments operating pressures exceed and therefore violate their updated ASME B31 design pressures and earmarks these segments for modification. If we look at figure 3, it is the ASME B31.12 design pressure formula, where the design pressure formula is a function of the pipe geometry and then various material performance factors. BlendPATH modifies the pipe segments with design pressure violations to accommodate hydrogen blending and meet pipeline network end use demand. What this means is we identify the pipes that have design pressure violations and then modify that pipe such that it can handle or achieve the end use energy demand. BlendPATH offers 3 methods that are used in industry to modify pipeline segments. The first one I'm going to talk about is direct replacement, which is the image in the top right corner. The direct replacement method maintains segment operating pressures by replacing any existing pipe with new pipe of the same nominal diameter, but it could be of a different grade and thickness such that it now satisfies the ASME B31.12 design pressure. So in the figure, we see that the highlighted red pipes were deemed violating the design pressure, and they were swapped out with new pipes with an appropriate grade or thickness such that it no longer violates the design pressure. The next 2 methods are parallel looping and additional compressors. Both of these reduce the segment operating pressure, but increase the volumetric capacity by other means. In the parallel looping method, as the name says, we add parallel loop parallel to the existing pipe. What this means is the existing pipe doesn't need to be it's not touched, and we add new pipe parallel to it such that we increase the hydraulic diameter. Next, moving on to additional compressors. In this method, we add additional compressors spaced throughout each of the segments such that we can increase the volumetric capacity by operating at higher pressures. After modifying the pipe, we perform an economic analysis such that we can compare the levelized cost of transport. BlendPATH uses publicly available resources to cost out the pipe and compressor stations. For the pipe, we consider material, labor, miscellaneous, and right-of-way cost equations. For the material costs, we use a price per weight from Savoy Piping Inc. for commonly used line pipe steel grade. So we calculate the volume and then the weight and then determine the material cost for these pipes. For the remaining components, which are labor, miscellaneous, and right-of-way, we take those cost equations from an Argonne National Lab paper from 2022, which have cost correlations for each of those components. So that's for any new pipe that's been added. We can also look at any compressors that have been modified, retrofitted, or upgraded. These consider material, labor, right-of-way, and miscellaneous costs from a 2011 paper, and those are all based on the capacity of the compressor station. All of these costs are coming from publicly available data and can be overridden with user input. We acknowledge that users are going to have more representative data for their specific case study. So we encourage users to input their own cost functions for a more representative case study. Those are examples of some of the costs or the capital that we put into the economic analysis. Then we compile this all into a financial analysis using ProFast. This is a Python version of H2Fast, which compiles capital, operating, and financing structure into a levelized cost of transport and provides a cost breakdown of each of those components. H2Fast is a freely accessible tool via NREL's website at the URL as shown, and BlendPATH is dispatched with the ProFast dependency. That's a high-level overview of the nuts and bolts of BlendPATH, and next we're going to go into installing and running BlendPATH. BlendPATH is an installable Python package and can be installed using pip. We recommend BlendPATH users have Anaconda and Git installed on their server or PC. And in addition, you also need Saint to run the hydraulic model within BlendPATH. The BlendPATH code can be will be hosted at github.com/nrel/blendpath and is downloadable by either downloading the source files from GitHub, or you can clone the repository if you're comfortable with the git bash terminal. That command would be git clone and then the URL to the repository. We also recommend users set up a virtual environment for BlendPATH, and this can be done through Anaconda. The 4 commands shown below would help set up such an environment, where first you're creating the environment, setting the highlighted text, the blue text, to the name of choosing, then activating the Conda environment. Next is moving or changing directory to where the files are hosted. If you clone them through GitHub, it's probably in the GitHub folder. However, if you download the source files, they may be in a separate location. Of course, check your own circumstances before proceeding with this step. And then finally, you can install it with pip install period. Check that you have the period at the very end, since this denotes that is looking at the current directory. Now it's installed, we also recommend that you use an IDE of your choice. We developed it in Visual Studio Code, so we know that works. Verify when you're using your IDE that you are in the environment name where you installed BlendPATH 2. BlendPATH has a particular file structure for running any of the specific case studies. On the left, I show an example file directory for a case study in BlendPATH. So if we have a working directory, within it, the first item is going to be a Python script. This will be used to run BlendPATH. At the same level, we're going to have a directory, and here I call it case study name. I highlighted it in blue just to denote that file name should be the same with any of the following files that have the same name. The first 2 files within this are going to be an event and network file. These are Excel files that are input files to describe the network and operating conditions of the network, and that's all particular to Saint. So that has a particular format such that Saint can interpret it. We do have examples of the network and event file within BlendPATH to help users create their own network and event files. The next file is the pipe mechanical properties. This is, again, an Excel file. This holds the specified minimum yield strength and the specified minimum tensile strength for each of the pipes. Note that the pipe names within this Excel file should also match up with the pipe names in the network file that is supplied to Saint. The next file is a .json file. This is an optional file that holds the ProFast economic parameters such as tax rates and financial structure. So once again, it's optional, not required. There are defaults in the tool. However, for everyone's economic analysis, customizing these may be more representative for your case study. The last file, the last directory is a results directory, which is where all the results from BlendPATH go into. And we'll talk about that later in this webinar. Once again, there are examples provided in the BlendPATH file directory, and that will be what we're going over in the live demonstration. Next, I'm going to go into the Python script that will run BlendPATH. This is a bit of a beast to go through, but I'll go quickly line by line. The first line is to import BlendPATH. This is importing the Python module or package. Assuming it's been installed correctly, this should be a straightforward Python import. The next line is that we're going to create a BlendPATH scenario. We're creating an instance of the class where it takes in multiple parameters. The first parameter is the case study name. Here we define it as Wong et al. 2018. And this is going to want to match up to the case study name directory that was supplied in the input files. We can also specify the save directory if needed. The next parameter is the design option. This is the ASME B31.12 design option to assess the existing pipeline. So once again, those options are A, B, and no fracture control, which we have specified here as no fracture control. The next two parameters are specific to ASME B31.12. You can specify the location class and the joint factor, which come into play into the design pressure equation. The next parameter is the compression ratio. This is the design compression ratio for any new compressors. The blending parameter is specifying the mole fraction of hydrogen into the blended pipeline gas. So the pipeline gas has already been defined, and then we're adding additional 20% on top of that to be blended in. I'll note that this is represented as a fraction, not a percent. So the 0.2 here shown is 20%. The next two parameters are financial parameters that define the natural gas and the hydrogen cost. The natural gas is defined in dollars per MMBTU, and the hydrogen cost is defined in units of dollars per kilogram. The next parameter is the final outlet pressure. This is in units of Pascal, and that is the minimum pressure at the model pipeline terminus. The final parameter I'm going to talk about is the design rating of existing compression stations in megawatts. So these names line up with the compressors in the network file. And this is to determine if any additional compressor capacity needs to be built out relative to the existing capacity. These are a lot of parameters that can go into the BlendPATH scenario, and it's not an exhaustive list. However, we recommend putting in as many as possible just to get most representative case study. These are all saved into a BlendPATH instance, and then the next slide will talk about how to run the modifications on that pipeline. Running a modification on the pipeline can be done by using the run mod function. This can take two input parameters, where the first one is mod type and the second one is design option. The options for mod type are the various modification options for the pipeline. These can be direct replacement, parallel loop, and additional compressors. Design option specifies A, B, or no fracture control, and this is for the design option that users anticipate to pursue qualification for new pipe with this certain design modification. So in the example shown here, I'm running a direct replacement method and using design option B for the new pipe. This is going to, of course, be swapped out with any other modification methods, such as parallel loop or additional compressors. The next line is to run the financial analysis on the modified pipeline. This has an optional parameter called cost overrides, which users can put in their own cost targets or cost points for certain items such as labor cost, and that can be defined in dollars per inch per mile, or specifying the original pipeline cost. Once again, those are all overrides, so there are defaults using publicly available data, but users can input their own data there. Final line is to print out the levelized cost of transport, and that's in dollars per MMBTU. BlendPATH will print out a few different files that summarize the analysis. So within the same case study name, we're going to go into the results directory that was specified in the when inputting into the parameters for making the BlendPATH instance. And then there's going to be two files beneath that. First one is network files, and the second one is result files. The network files are going to be the saint, network, and event files of the modified pipeline. So if a direct replacement was performed, then you'll see the updated new pipes that were replaced. This also will include any updated inlet pressures, updated to the maximum allowable operating pressure, and then any updated compressor outlet pressures or compression ratios. In addition to that, we also print out a BlendPATH summary file. Within here is a readout of the input variables, the financial inputs and outputs, capital expense and operating expense breakdown, new pipe and compressor design, and then demand errors, where we're specifying demand errors as the percent unsatisfied energy end use demand within the network design. And this is just a validation check that the end use demand has been satisfied. I talked about the BlendPATH summary file, and this is a quick overview of what's within that file. Actually, I'll quickly start at the bottom so this is an Excel spreadsheet. There's going to be 5 different sheets in there. The first one is the disclaimer, which talks about the capabilities and limitations of the BlendPATH tool. Next is the input, so that's a readout of all the inputs that went into the BlendPATH simulation. The result, which I'll talk about in a second, the new pipe design or a new compressor design based on which modification method was performed, and I'll outline the geometry and operating conditions for the updated values, and then the demand errors, which once again is a validation that end use demand has been satisfied. The first box is the summary values. This is a high-level readout of many of the values within BlendPATH. For example, the first one on the list is the levelized cost of transport in dollars per MMBTU. This can also be broken down into various components that highlight some of the capital items, fixed O&M, taxes, and financial. The next box below is the cost breakdown of new pipe. This is a readout of any new pipe that's been added and the geometry of it. So you can see the diameter, length, and then also the grade and schedule. In addition to that, you can also look at the material cost, labor cost, miscellaneous, and right-of-way cost. In this scenario, the right-of-way cost is 0. That's because this is for a direct replacement, so we're assuming that the right-of-way has been used, the same right-of-way is used for the new pipe. The next box is the breakdown of the original pipe. This is a reminder of the input, the incoming pipeline. So you can look at the pipe diameter, length, grade, and schedule once again. Next is the cost breakdown of compressors if they are apparent in the pipeline network. This can include shaft power, the rated capacity, and then also fuel usage. With that, I'm going to go into the live demonstration. The live demonstration is going to go over an example file that we have prepared. And this is a modified version of the Wong et al. 2018 case study, where the link, the citation to that paper is in the footnote below. This case study is a 250-mile pipeline over negligible elevation change that consists of a single diameter, grade, and schedule. The modified case study is distributed as part of BlendPATH and can be found in the example files at the directory shown below. Table 3 and 4 show the geometry and operating conditions of this pipeline. So table 3 shows the 4 segments within the pipeline, and you can look at the diameter, schedule, grade, length, and design pressure. And then also you can look at the outlet pressures of all the compressors, the supply pressure, and the offtakes within that pipeline network. And now I'll switch over to a different screen if you bear with me just for a second. Okay, let me share my screen again. Okay, so this is showing a blank Visual Studio code. So as I mentioned, the examples is part of the BlendPATH tool. So if you navigate to where the source files are and navigate into the examples file, we have a template Python file and then this case study directory. Within here, I can open it and we'll see the event file and network file. Those are input files for Saint, and then also the pipe mechanical properties. I'll open up the network file just for example. This has a lot of parameters that go into specifying the network. Some sheets to pull out, or like the GNO, which specifies all the nodes within the network. And we can also specify all the pipes within the network, any compressors in the network, and also demand and supply. This is a fairly involved sheet to go through at this time, but of course, this is available for any user that downloads BlendPATH for an example and to base their case study off of. Next, if I go to Visual Studio Code and open if I go to the examples once again, we can open up this template.py. This should be fairly familiar as this is the screenshot in the slide was taken from this file. So I won't go through all the points within this slide. However, I will once again note that this is running a direct replacement method with design option B. So if I run this script, first thing we're gonna see is the disclaimer readouts. And once again, this is a reminder of some of the limitations and capabilities of BlendPATH. Next, what's gonna happen is gonna run the hydraulic model for the original pipeline. Want to note that, want to check that the simulation has completed so that it can be seen as a steady gas simulation completed successfully readout, and that's coming from the Saint hydraulic simulation. After that, we modify the pipeline and then we rerun the modified pipeline in the hydraulic model once again. And as we can see, once again, the simulation completed successfully. The final readout is a high-level readout of the levelized cost of transport, and that's so 18 cents per MMBTU. And that's just an example for the coming out of the example file. So now that's run, let's take a look at the result files. So I specified the outlet or the results directory as out, and then no fracture control. And then within network files, that's going to be the updated network and event file. And then result file is going to be the BlendPATH summary files. I've already pre-ran a few of them here, but for the example that we have just shown, which was direct replacement denoted by DR, and then 0.2 for 20% blending and no fracture control. This is an Excel file, and like I mentioned before, there's a disclaimer, there's inputs. This is a summary of all the inputs that were put into the BlendPATH simulation. These are all specific to BlendPATH, and then below is more financial related parameters. Next is the results. We've already talked about this during the slide, but we can see that there's an outline of the new pipe, original pipe, and of the compressors. Since this was a direct replacement method, there's going to be a new pipe design that we can go to here. And this outlines any new pipe that was added, what the dimensions are, the grade, schedule, and what the updated maximum allowable operating pressure is. Next, if we go to demand errors, we can see we outline the demand flow target and what the simulated demand is. This shows the error, and this should be as close to 0 as possible, signifying that end user demand has been met. With that, I'm going to head back to the presentation, and I'll hand it off to Kevin.
Thank you, Jamie, for the transition. So in addition to this webinar, technical documentation on BlendPATH, which will detail some of the parameters or all the parameters that we discussed as part of this webinar, as well as the example. This will be published as a freely accessible NREL technical report, and we'll go into more detail on the aspects that we discussed today. Once this technical report is published, we will be adding this to the source code that we will be making available through a GitHub repository. The BlendPATH source code is to be hosted via this link through NREL's GitHub organization account on GitHub with this link github.com/nrel-blendpath. And we expect the code to be made available in the coming weeks. If there are any questions regarding BlendPATH itself or this webinar, please direct your questions to me after this webinar at this email, kevin.topolsky@nrel.gov. Lastly, I would like to mention that BlendPATH is a result of our effort in phase 1 of HighBlend, and at this point of the webinar, I'd like to thank our industry partners as well as Department of Energy for supporting us through phase 1 and providing input for BlendPATH. I would also like to share that currently phase 2 of HighBlend is currently being planned, where we will be furthering development for BlendPATH, in addition to other scope items that will include advancements in materials and analysis topics for research regarding blending hydrogen into the natural gas pipeline system. Partners to this phase 2 will gain access to pre-published research and can provide input on scope, as well as gain access to lab expertise. So if you're interested in learning more about being a phase 2 partner, please contact us via this email, highblend_CRADA@nrel.gov for more details. But with that, thank you for your attention and being present for this webinar, and we'd be happy to address any Q&A